Today we have alternating series. An alternating series is a series whose terms are alternating positive and negative. So for example, on this first one, it goes 1 minus 1/2 plus 1/3 minus 1/4. And this right here tells us that it's alternating. And we also have, it can start with a negative also. In general, just knowing that a limit as n approaches infinity of a sub n equals 0 tells us very little about the convergence of the series. However, it turns out that an alternating series must converge if its terms consistently shrink in size and approach 0. So we have the alternating series test. If a sub n is greater than 0, then an alternating series converges if both of the following conditions are satisfied. Limit as n approaches infinity of a sub n equals 0, and a sub n is decreasing sequence. That is, a sub n plus 1 is less than a sub n. In other words, the next term is less than the previous term. Now, this is just the nth term test. It has to pass the nth term test. Note, this does not say that if the limit as n approaches infinity of a sub n does not equal 0, the series diverges by the alternating series test. The alternating series test can only be used to prove convergence. Alternating series test can only be used to prove convergence. If the limit as n approaches infinity of a sub n does not equal 0, then the series diverges by the nth term test for divergence, not by the alternating series test. Now, the way an alternating series works is you add, let's say, a positive number. It could be going the other way and add a negative. Let's say it's positive. Then you minus the next number, and then you add the next number, minus the next number. And what's happening is you're converging to the sum, but you're converging on opposite sides. So you're approaching it from both sides. But the magnitude is getting smaller to the value. So for example, if we went 1 minus 1/2, and get that value, plus 1/3, minus 1/4, plus 1/5, minus 1/6. Look at the numbers. Plus 1/7. So now we're on the, plus 1, what happened there? Plus 1/7, insert 1/7. Now we're on the other side of the number. Then we minus 1/8, and we're on the other side of the number. This is actually converging to, you would think 0.7 would be reasonable, but it's actually the natural log of 2 that we're converging to. So it's going above and below 0.69 infinitely, but approaches the value. Determine whether the following series converge or diverge. Here we start out, this is an alternating series, so we start out with the limit as n approaches infinity of n over 2n minus 1 is equal to 1/2. Well, that's not 0. So this diverges by nth term test. Over here we have what's called the alternating harmonic series. And we can do the limit as n approaches infinity of 1 over n. We ignore the fact that it's -1. As a matter of fact, it's really the absolute value is equal to 0. So it passes the nth term test. Now, can we say 1 over n plus 1 is going to be less than 1 over n? Sure. If we have a bigger denominator, we have a smaller fraction. So now we can say converges by alternating series test. On the third one here, B, we have, we do the nth term as an alternating series, limit as n approaches infinity of n over natural log of 2n is equal to infinity. So n outpaces natural log. So natural log looks something like this, n looks like that. So n is outpacing. That is not 0, so diverges by nth term test, not alternating series test. Here we have cosine of n pi over n. So we plug 1 in, cosine of pi is -1 over 1, which is, let's start out as -1. Plug 2 in, cosine of 2 pi is 1 over 2, minus, plug in 3, and that is cosine of 3 pi, which is -1 over 3. So plus 1/4 minus 1/5. So this converges by, and you can do this, you can say converges by alternating harmonic series, and you don't have to show the work. Converges by alternating harmonic series. Here we have the limit as n approaches infinity of n over n squared plus 10, which is equal to 0. The denominator is winning the race to infinity, so the fraction goes to 0. But if I have n plus 1 over n plus 1 squared plus 10 is less than n over n squared plus 10, if the numerator is changing and the denominator is changing, it's hard to tell if this is actually a decreasing sequence or not. So we're going to let f of x equal x over x squared plus 10. Then the derivative is bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. So we're going to take the derivative, and if the derivative is negative, that means the function is a decreasing function. So that's equal to x squared plus 10 minus 2x squared. The denominator is not going to contribute to the sign because the denominator is squared. That'll always be positive. So we have 10 minus x squared over x squared plus 10 squared. And we want to know when that's negative. Well, that'll be negative when 10 minus x squared is less than 0. So we have negative x squared is less than negative 10. X squared is greater than 10, so x has to be greater than square root of 10. But with n, so this is happening when x is greater than or equal to 4, because square root of 10 is between 3 and 4. Alternating series remainder. Suppose an alternate, oh, I didn't finish the other problem. Converges by alternating series test. Alternating series remainder. Suppose an alternating series satisfies the conditions of the alternating series test. Namely, that the limit as n approaches infinity, base of n equals 0, and the sequence is a decreasing sequence. If the series has a sum, then the remainder is, this would be exact minus the approximation. So if you take what you think is the approximation and subtract the exact value, that gets your error, or in this case, your remainder. In other words, if an alternating series satisfies the condition of the alternating series test, you can approximate the sum of the series by using the nth partial sum s sub n, and your error will have an absolute value no greater than the first term left off. So if you, here we have approximate the sum of this series by using its first 6 terms and find the error. Use your result to find an interval in which s must lie. All right. So if I plug 1 in, 1 minus 1 is 0. So we get 1 over 1 factorial. That's 1. So let's make it 1. Then we have plug 2 in, and we get a negative 1 over 2 factorial, which is 2. And then plus 1 over 3 factorial, which is 6. Minus 1 over 4 factorial, which is 24, plus 1 over 120. First 6 terms. 1, 2, 3, 4, 5. Minus 1 over 720, and then plus, keep on going. What are we doing? Use and find the error. Use your results to find an interval which s must lie. So we're approximating and find the error. So let's get what this is equal to. 1 minus 1/2 plus 1/6 minus 1 over 24 over 24 plus 1 over 120 minus 1 over 720. And that's what we get. So the estimate to this series is 0.6319 and then a bunch of 4s. Find the error. The error is going to be less than the first omitted term, which is 1 over 7 factorial. So the error is going to be less than that first term that's left off. So 1 divided by math, probability, oh, wrong one. 1 divided by 7 math factorial. So the error, the most the error can possibly be, and they call it an upper bound, if you see that phrase, upper bound, the highest error we can possibly have is 0.0001984126,984. That's the most error we can possibly have in this approximating that. Use your results to find an interval in which S must lie. If I guessed that you had $7 in your pocket, and then you told me, well, I'm at the most $2 off, then I could take the approximation, add on the error, and that would be 9. I could take the approximation and subtract the error, and that'd be 5. So if I guessed 7 and you said, well, at most your error is 2, then it could be $5 at least and $9 at the most. So that's exactly what we do here. We say that the actual sum is between two values. And this is the approximation minus the error, and this is the approximation plus the error. And that gives us an interval where the actual value has to lie. So let's take the approximation and minus the error, or what could possibly be the error. So 0.63174,60317 is less than the actual value, is less than. Now we're going to take the approximation, which is up here, and add the error. So 0.6321428,571. Approximate the sum of the next series with an error less than 0.001. If we plug 1 in, we get a positive. So 1 over 1 to the 4th. Let's call this 1 as well. Then we have minus 1 over 2 to the 4th, plus 1 over 3 to the 4th, minus 1 over 4 to the 4th, plus 1 over 5 to the 4th, minus 1 over 6 to the 4th. So if we stopped, if we said, well, this right here is going to be our approximation, then the most our error could be is this right here. Now if we take 1 divided by 4 to the 4th, the error is 0.003. That's 3 thousandths. And that's more than 1 thousandth. So we got to keep going. So let's say I want to use this much right here as the approximation. And now this is the most error we could possibly have. If you take 1 divided by 6 to the 4th, that is actually less than 1/1000th. So 1 over 6 to the 4th is equal to 0.0007716, let's say. Now that error is less than 1/1000th. So the approximation is 1 minus 1 divided by 2 to the 4th plus 1 divided by 3 to the 4th minus 1 divided by 4 to the 4th and plus 1 divided by 5 to the 4th. The approximation is 0.947539429 and has an error less than that, which is less than 1/1000th. Now there's another way to get the fact that you would have 6 as the number. 6 right here. We're thinking 1 over n to the 4th has to be less than 1 over 1,000. So we cross multiply. So that's n to the 4th, multiply over here, that's 1,000. So n is greater than the 4th root of 1,000. Well, if we take the 4th root of 1,000, math up here, then we get n has to be greater than 5.623, which is the next integer, which is 6. The Maclaurin series for natural log of 1 plus x is given by that series there. On its interval of convergence, this series converges to natural log of 1 plus x. Let f be the function defined by this, which has a 1 plus x has been replaced with x plus 3 right here. So the x has been replaced with x over 3, and we're also multiplying times x. Write the first 4 non-zero terms in the general term of the Maclaurin series for f. Well, let's put x over 3 in for that x, which means we're going to put x over 3 in for all of those x's. So x over 3 minus x squared over 3 squared times 2 plus x to the third over 3 to the third times 3 minus x to the fourth over 3 to the fourth times 4, and so on. So plus dot, dot, dot. But now we're going to multiply all those by x. So now we have x squared over 3, x to the third over 3 squared times 2, x to the fourth over 3 to the third times 3, minus x to the fifth over 3 to the fourth times 4. Need the general term, plus dot, dot, dot. So let's start with, I don't know, how about we start with 1? So that's going to be negative 1 to the n plus 1, because it starts positive, x to the n plus 1 over 3 to the n times n. Determine the interval of convergence of the Maclaurin series for f. Show the work that leads to your answer. Let's use the ratio test to find the interval of convergence, since it's not geometric. Limit as n approaches infinity, absolute value of x to the n plus 2 over 3 to the n plus 1 times n plus 1 times 3 to the n times n over x to the n plus 1. Yeah, there we go. Well, now we have the limit as n approaches infinity, absolute value of, there's an extra x on top, there's an extra 3 in the denominator, n over n plus 1. Now we're doing the limit on n. So we end up with x over 3. Absolute value of x over 3 has to be less than 1. So negative 1 less than x over 3 less than 1. Negative 3 less than x less than 3. So the interval of convergence is negative 3 to 3. Let p sub 4x be the fourth degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for p sub 4 of 2 minus f, which is approximation minus the exact. So really, and they probably even use the word error. Actually, yeah, the series error, which is also called the upper bound. What's the highest error you could possibly have? Well, we're doing this with fourth degree, which is not the fourth term, it's the fourth degree. So we're saying we're adding those up. So this is going to be the error of the fourth degree. So the fourth degree error is the fifth degree term. Now look, we're doing this at 2. So we're going to go, the error is actually less than the absolute value of negative 2 to the fifth over 3 to the fourth times 4. And that is equal to 32 over 81 times 4. So it's 8 over 81 is the highest error we could possibly have for that fourth degree approximation. Determine whether the following series converge or diverge. This is alternating, so we're going to do the limit as n approaches infinity of n over 3n minus 1. That's 1/3, not 0. Diverges by alternating series test. So this is kind of a repeat of what we just did, just a little more practice. The limit as n approaches infinity of 1 over square root of n, that's equal to 0. And 1 over square root of n plus 1 is less than 1 over square root of n. So this converges by alternating series test. This one has the top and the bottom is increasing, or decreasing, excuse me. So let's do the limit as n approaches infinity of n over n squared minus 1, and that's equal to 0. So it passes the nth term test. But now, in order to say this, we have to do the derivative. So we're going to let f of x equal x over x squared minus 1. F prime of x is bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Which is, if we take x squared minus 2x squared, we get a negative x squared minus 1 over x squared minus 1 squared. Now normally we do this, negative x squared minus 1 has to be less than 0, but look what happens. We add 1, divide by negative 1, and we get greater than negative. Now we're trying to try to square root negative 1, so there's a problem here. And the problem's not really a problem. If you take negative anything squared, like 2 squared is 4, and then minus 1, that's negative 5. So this is negative for all values. So this is true for n greater than or equal to 0. So it starts decreasing right away. We don't have to wait for it to decrease at a certain point. Find the power series representation for f of x equals 3 over 4 plus x centered about x equals 2. Also specify the radius of convergence for the series. Find the power series representation centered at x equals 2. So f of x, this has to say 3 over 4 plus x minus 2. I need that x minus 2, but I can't just subtract 2 to a denominator. We got to add 2 also. So this is 3 over 6 plus x minus 2. Now that's centered at 2. But I need this to be 1. So 1/2 over 1, how about we make it minus 1x minus 2. So minus minus gives us the plus. So a sub 1 is 1/2, and r is negative x minus 2. So what are we doing? Find the power series representation centered around x equals 2. So a sub 1 is 1/2. Then we have minus 1/2 x minus 2 plus 1/2 x minus 2 squared minus 1/2 x minus 2 to the third plus keep on going, and that's going to be negative 1. What if we start at 0? Negative 1 to the n, x minus 2 to the n, and what do we need? We needed 2 in there somehow, and that's just going to be over 2. So also specify the radius of convergence for the series. R is right here. So we need absolute value of x minus 2 to be less than 1. So negative 1 less than x minus 2 less than 1. Add 2. 1 is less than x is less than 3. So there's your interval of convergence. Give the first 4 non-zero terms and the general term for the series for the function f of x equals 2 minus 2 cosine 3x. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, x to the 6th over 6 factorial. Cosine of 3x is 1 minus 9x squared over 2 factorial plus 81x to the 4th over 4 factorial minus, let's go, 3 to the 6th, x to the 6th over 6 factorial plus keep on going. Now we're going to multiply everything by 2. So how about multiply everything by, should we go negative? Let's just go 2. 2 cosine of 3x. So 2 minus 2 times 9x squared over 2 factorial plus 2 times 81 x to the 4th over 4 factorial minus 2 times 3 to the 6th x to the 6th over 6 factorial. And now we're going to go 2, and we're going to run a negative through this. So 2 minus 2 plus all of this kind of opposite sign now, times, minus 2 times 81 x to the 4th over 4 factorial plus 2 times 3 to the 6th x to the 6th over 6 factorial. So the 2's cancel, gone. So now our series is n equals, let's see, what should I start with? I think I'll start with 1. 1 to infinity of negative 1 to the n plus 1. Everybody has a 2. 3, this starts at 3, what does it start at? It starts at 3 squared and 3 to the 4th and then 3 to the 6th. So 3 to the 2n but it starts at 2, 4, and 6. So minus, if I plug 1 in, oh, that gets 2, doesn't it? When we plug 1 in. Ooh. Yeah, we plug 1 in, we get 2, 2 in, we get 4, and so on. Got it. Got that piece. And then over 2n factorial. Yeah, we found the general term as well. Actually, we found the series.